put it and I will say better, no?
Looks like those concepts are the most of the
Thank you.
Today we have very different topics. Would be interesting from my friend and colleague Professor Nithin Nagaraj, who is National Institute of Advanced Studies, which is part of the IC campus, and very interesting topics. I'll let them.
Okay. Yeah, firstly, let me thank Chetan for this invitation and wonderful workshop that you have organized. So these days, I start my talks with the disclaimer, you know. So, okay. I mean, I know it's like you start a movie, you start a disclaimer, right? That just to make the point that they were all made by me, myself, and the resemblance coincidental with any LLMs, output of LLMs. And last but not the least, I thought, I know it may seem we probably have to do this in the next few years, right? That no harm was made to any robots while making this presentation. Okay, so having said that, what I want to do today is try to sort of give you the central crux of this talk, which is chaos plus noise is learning. So, and what is the chaos part, what is the noise part, and how. So that's going to be the theme, and then we look at some applications of this what we call as neurochaos learning, and feel free to stop me, you know, as we go along. Yeah, I think this is a problem you've seen umpteen number of times, right? You take lectures, YouTube, I mean talks, tutorials, you see this kind of a diagram, and the claim is made that there's some level of mimicry of the brain, I mean at some level, and that's how learning, right? But what is interesting is that in the recent past, I think this is quite amazing, right? That it's led to Nobel prizes, both in physics, chemistry, and as well as medical. You know, the Lasker Prize, for example, and mathematics is not far behind. So we are clearly in the not deep learning. I mean, it's so specific that that all these technologies use pretty much only deep learning, right? More or less. I mean, you can say that the other sort of fallen out of practice, and of course the applications. But this is probably important. We know the problems. We all know the problems of deep learning systems, right? Extremely data hungry, very easily, not easy to interpret, and we will see in a very specific case why it's not easy to interpret in terms of causal reasoning, and we know about computational resources and other stuff. I thought I'll just play this. You know who said this? I mean, probably many of you probably can guess. In the world number, the most top rated chess player said this, so you probably know whom I'm talking about, right? Yeah, Magnus Carlsen, right? That it's we have on our mobile phone. Now it's okay with this sort of very initial. Do you recognize this Nobel laureate? He said this. So the question to the especially you to sort of who is this Nobel laureate and what is he talking about here? My view is to throw again. Any guesses? Yeah. What is he referring to? He said this statement in 2018-19, I think. He was referring to his own work, to the backpropagation algorithm, So he was saying that, it's like the cockroach if it refuses to die, and his point was that maybe we need new ways to look at it. I think it's a very interesting point, right? That we have transformers and we have LLMs. They all use this algorithm, right? You have to use it, right? I mean, one way or the other. But he was arguing that that maybe some fresh undergrad or grad student will come and rethink the whole thing and come with a new paradigm. So I thought this was an interesting quote, and right, that essentially something has remained pretty much the same since 1943. Do you recognize these two gentlemen? Again, very important to the topic that we are talking about. One is a logician, and they wrote this very important paper in 1943, which even till today a sort of reaping the benefits or you know, of this paper. Any guesses on? Yeah, they talk about the computational model of the neuron, and what is very interesting is that the neuron has not changed much, slightly maybe. Neuron with, but it's essentially the same, right? You just do some kind of W transpose X plus B, and then you pass it to some activation, right? So essentially the neuron since 1943, more or less, you know, the same neuron that all these are on basically, right? So that's an important thing to note because obviously, right, that maybe we should start from the neuron, away the neuron and start afresh. So and then probably you probably know this, but I think maybe there are some students who are beginning in the field, so it's good for them to know the dark side of generative AI. I think it's good to know all kinds of numbers. 179 billion parameters, and these numbers are probably conservative numbers, right? I mean, the numbers are growing by the $4.6 million for training. Then you have running costs. Then you have this kind of energy consumption. I mean, the numbers are really crazy, right? It's good to probably know these numbers because we are going to now compare. We're going to see why the brain is not at all like this, and point. I mean, again, these are again, you know, sort of catchy numbers to look for, but I think the kind of radiation, the kind of you know, heat consumption. So you want to cool these servers, right? And of course, these numbers are even crazy, you know. And I think these again, these numbers are probably even more scarier. I think I heard the whole of Europe, I think at some point, you know, could be powered. I think at some point, right? So here we're talking about 3 months of power consumption of New Zealand and, you know, things like that. So it's good to know, I think, if you're a beginner in the field, it's good to know where we stand in terms of, and then I think people who using LLMs, don't be courteous, right? Don't use thank you, sorry, please, don't use that. I mean, it's just going to burn, melt the CPUs, right? Now, what is very interesting is that there was a study done in 2019, actually. It's a dated. The study is quite important. Known that, and they were doing it on GPT-3, I think, if I'm not mistaken. GPT-3, they were arguing that vision is just training it once. Training it once is burning 5 carbon. It's the carbon emissions of 5 cars for their entire lifetimes, right? That's and then they. If you look at the numbers, these are again the transformer with 2. Look at it; it's million. It's not even billion, right? I mean, it's quite a small network. And these are the kind of numbers that look at the carbon footprint, and you look at human life. I mean, way less, right? And there are other numbers as well. So I think it's good to know these, and then maybe we can take Hinton's thing seriously. So let's start all over again. So first thing we have to do when we start all over again is recognize that this is not the truth, right? So there is no that these networks are remotely close to the brain, right? I mean, it's going to be like, I mean, it's really a mistake to compare these networks with the brain, and I'll tell you, right? So you'll see, but of course, I mean, you and me, we had the benefit, right? So we are the you know, 3.8 billion years we had that, and you see the kind of numbers our you know, animal kingdom you know, has these kind of numbers, right? Look at, and we're talking about the cerebral cortex here, 9.1 billion neurons. So these numbers are numbers, right? And of course, we at this point of these kind of numbers in terms of the complexity of neurons, but it doesn't end. What's interesting is the connectivity, right? That's the key, I think, you know. Each neuron is connected 100 to 10,000 neurons. I mean, I'm not a neuroscientist, but that's what I hear. And if you do the math, it's 100, and we're talking about 86 billion neurons. So if you look at it from just the number of neurons, galaxy, but we are far more complex than the galaxy. I think it is important because students especially the senior PhD students, you know, I mean, they're very depressed. You know, they say that, okay, how will I get a job? I don't have connections. I say you have connections, you know, you just have a galaxy worth of connections in your head. You just, there's no reason to be depressed, you know. I mean, what I'm saying is that we have to tune our network, right? I mean, so I think it's important. These numbers, look at these other. Okay, let me ask maybe the audience, right? What do you think is the signal to noise ratio at a neuron in the brain? Some numbers can you give me? The signal to noise ratio I'm talking about here, you know. What kind of numbers you want to give? 0 dB, okay. That's starting point. It's like an auction I'm doing now. Who you want to go? Basically, and the noise levels are the same. That's what he's saying, you know. It's very impressive, even if that's the case, right? Any other candidates? Anybody wants to go up? Anybody wants to go down?
Find what signal is. What signal in this case?
That's a good question. So, I mean, the point here is that any signal which we can model the functioning of the brain, right? Maybe you're doing some cognition or attention, you in a context. But I'm going to give you the reference to Epina's paper where they do this rigorous manner. But the answer is quite scary, you know. The answer is it's astounding. It's minus 29 decibels. You can read, compute this number. We're talking about minus 29 decibels and minus 29 to minus 20 decibels. The noise that's way so-called, and the ChatGPT was some 1,000 to 1,200 megawatts, I guess, or gigawatts, megawatts, I guess, right? Yeah. So what is the number here? What do you think is activity, a simple thinking activity? And you can compute the number, sort of how much of metabolism is there in the brain and how much is the rest of the body, and then you can actually compute sort of roughly what kind of activity will take. You can do this computation. So a few hundred starting number. Do you want to go? You want to go? 20. No, around 12.6 watts. Again, the computation. I mean, take there, you know. Look at this amazing thing. Now we have extreme at one side of the story, and the other side of the story we have, you know. It seems like a contradiction, right? Do you know of any human engineering system which has this combination of contradictions, right? How can you have and so low SNRs, you know? That's the thing. And there is multiplexing, by the way. If you know, if you study communication theory, right? Multiplexing is not a but multiple signals.
Prior information that should be okay, like lock-in amplifier people use in RF.
Right.
I mean, signal to noise is very low.
Very low.
You have some information, then you can recover.
So maybe here also we have some models and we have some background. I don't know. But even then, would it be this low? And the kind of work that the kind of the activities the brain does. Okay.
If you have some other information, if you don't have any information, yes, it's very difficult, right? And typically
Right.
when you have
Right.
SNR, if you need higher SNR, you have to burn a lot of power.
Correct.
It's the same, but if you have some
Prior information, that could help.
You can extract with much.
That's a good point. And the question still in an efficient manner, given this complexity that we're talking about is huge, right? Trillion, right? But that's a good point. Now, now the question is how does, and I know making the works. I'm saying an extreme thing, but you don't makes this point that brain science is still at a Faraday. So you look at how different domains. Now, what he's comparing to, of course, physics here. So what he's saying is that we still don't have a Maxwell theory of electromagnetic Faraday stage, in the sense that exactly principle on, you know, that there is, okay, this is how the brain really works. So in that sense, I think we don't know much. It's a good thing. It's a good job security, I think, you know, for if you want to work in this field. And I thought I'll just give you a simple piece of code in Python. You take a neural network with one hidden layer, and I'm just looking at a three-class classification problem, right? The famous the iris. I mean, this is a data set that we all sort of work with when you start off learning machine learning, and you add a noise to it, you add, you ask the question, where does it collapse? So, like performance is very, very poor. So I'm saying that even at around 8 decibels, it just collapses, you know, and look at the degradation is not very graceful either, you know. It's not like a graceful degradation. So here I'm after you learn, so you do a excellent, and then you start adding noise to the weights and biases, and that's what happens, you know. So sort of to this is the brain on one side, on the other side. What is important to understand is that it's just linear neurons, right? It's just linear processing with nonlinear activation, right? Whereas the brain uses completely different mechanisms, right? And we're going to study that in some detail today. And what is very interesting is that neurons, right? I mean, you may change the activation functions, you can try to bring in heterogeneity, but the brain is known to have inherently heterogeneous neurons depending on the function, the location where it's situated and things like that. So there is heterogeneity, and there are other things which I've already talked about. And it's also interesting that if you ask the question, is the brain digital or analog, right? It's sort of a mix of both and maybe something beyond and massively. Okay. Now the point is that, as I told you earlier, that this is what we want to question. We want to question the core deep learning, the 1940 Macaulay-Pitts neuron, and slight modification to that. That's the neuron which is here basically. That's the neuron which is here, and that's the building LLMs and everything, you know. But like that whatsoever, you know. And these are two very good papers which encourage especially the student participants to read. Is there chaos in the brain? Part 1, Part 2, and for this paper in 2001 and 2003, where they talk about empirical brain, and I'm going to tell you very soon. So the argument is that the brain, the biological, nowhere plus B neuron, which is there in the ANNs today, you know, it's completely different. That's the point that you need to remember. And these papers, the term the word neurochaos. It's a term which is used by the authors. We borrowed the. Okay, can we mimic this? Can we take the chaotic behavior of the neuron? So in that sense, you know, we're not really other aspects of the biological modeling of the neuron. You know, there are computational models of the biological neuron. We're just taking the chaos part of it and then saying, okay, I just take the chaos part. And can we use that for machine learning? And that's what. But what is chaos? And by the way, network of neuron chaos. And by the way, you have the PQRST ECG wave, right? You have the RR tachogram. If you look at the RR tachogram, the RR interval is known to be chaotic, regular. And there is a benefit, there is an evolution, because we can quickly adapt. The beauty of chaos is that you can, but periodic behavior, you can have unstable behavior, you can have, I mean, you can do whatever you want. If you are in, whereas if you are in a random stochastic, or if you are in a regular, it will not be that easy. Okay. About chaos. And I thought the best way to show you chaos is to, and I'm going to a very simple example, and then we will go to the rest of the presentation. So what I'll do is just opening an Excel sheet, and you can all try this back later as well. I hope it's visible. It's visible in the back, so I'll start with number 0.2. Can you see in the back? You can see. Okay. What I'm going to do is I'm going to take this guy. I'm going to take this. The next cell, right? I'm taking the previous number 0.2, multiplying by 16 and subtracting 3. Is that fine? So I'm taking the previous cell, which is 0.3. I'll get 0. In Excel sheet, you can just do this, right? You can just drag it. Notice something very interesting, right? As I drag it, it should just be. So, I mean, you can drag it further and see what happens. It just explodes, right? We started with 0.2, and it seemed to be 0.2 for some 3, which is just 0.2, right? And then it explodes. It explodes and it goes all the way. I mean, in this example, it explodes far beyond the number. take 0.25 and let me take this guy and multiply by 5 and subtract 1. So, I am taking 0.25 and I am taking 0.25 I am multiplying by 1. What will I get? I will get 0.25, right. Now, you can play this when you can play, you know. So, how much explode? If I am going to drag this, I am going to drag this beyond, will it explode? And you can, you know, but chaotic principles, like you have this, you have the nonlinear pendulum, right, with magnetic bobs, and then you have the, I mean, there are and with the chaos theory in principle, you know. So, very good, interesting, sir. Answers. So, he is saying that it depends upon the thing, right, that what is the chosen number 0.2 and 0.25. So, it does not matter what computer, that the second one, right. So, how many of you want, I mean, there are no takers. Okay, I see one hand, I see a few hands which are saying it will explode. No, it will not explode, right, it will not, because it does not matter what computer you are going to run this. Okay, in F, both of them seem to be linear equations, right. I am doing 0.2 minus 3 and I am doing 5 minus 1. Both, this gentleman said, there is a storage in the computer, right, there is going to be round off errors, which is the nonlinearity, and that leads to this kind of an explosion. But the explosion does not happen here though. Why? I mean, that is the question you need to think about, right. So, think about it and keep that, and that is the, this is exactly what is. So, having nonlinearity and being, right, you do not want to go to infinity. Of course, this example, if you are sort of going off to infinity, it is not really, you have some kind of a finite length buffer exceed that. So, you are going to come back, you are going to come back to the you know, number system there. Now you probably know that it is good to know, and the Tamil movie 12B where the hero is you know, he is right, that, so there are some people here, right. Now, the two, right. So, that is sensitive dependence on initial conditions, right, and you probably heard of the butterfly effect, that the flapping of the wings of a butterfly in Kanyakumari can cause a snowstorm in Kashmir. It is actually not a statement, it is a statement of prediction, you know. That means that small error cannot lead to prediction, would have been the case, you know. That is, it's a statement of causation, but that's how it's stated, that the fluttering of the wings of the butterfly caused in Kashmir, right. Now, what is very interesting is that, remember that chaos is all deterministic. This is, I mean, the way chaotic systems are designed, there is nothing random about them, there is nothing stochastic about them, there are no coin tosses, there is no Markov process, nothing, you know, it's just deterministic equations. But the one example I showed you on the Excel sheet, right, that I am just doing a simple, right, I mean, there is no randomness there, there is no coin toss there, but, right, the precision and the rapidity. So, you 0.25, right, in my example, right, that's where the answer lies. So, that is the thing, and it looks and feels like randomness, but it's full of order and structure, okay. And then we can get into the technical details of chaos. I mean, you can read it up. It's, I mean, for this particular topic, any detail here, you can read. Give you some examples, right. Now, there is one dimensional maps, you know, which are very interesting maps. They just, you have a single variable and you on that, and it exhibits all kinds of funky behavior, you know. And is there an example of a one dimensional map which all of us, so the question I was thinking is there an example of chaos? The answer is yes. The answer is, so we all, class 9 we studied in class 9 textbook. In fact, I'll show you the page number of the textbook as well. We are, and which actually talks about chaos. I mean, it doesn't use the word chaos obviously, but I mean they could add that, and this is what that looks like, right? You start with the number, okay, that's the input. You output x, so you take x, you multiply by 10 and of 10x, you replace as integer part of 10x, and then you go to make it. So you start with 1 by. So what is the first step? You multiply by 7, and the red color, it's the output here, and you're going to replace 10 by replace 10 by 7. You get 3 by 7. In the next iteration, same thing, right? 30 by 7, output the integer part 4. Subtract 30 by 7 with the integer. Do this, right? And this is what you get. You start with 1 by 7, you go to 3 by 7, 4 by 7, to 1 by 7. And since it's a deterministic map, it will repeat. There is no randomness, right? So forever, you know. Notice 1, 4, 2, 8, 5, 7. Now, can you recognize what you studied in 9th standard? In the class 9 textbook, you did study this. What is this 1, 4, 2, 8, 5, 7? The decimal expansion of 1 by 7, right? I am just doing long division. I am just doing the integer, the decimal expansion of 1 by 7. That's all. Page number 9. Now, what is interesting is that this algorithm I showed, all the elements, it has periodicity, it has non-periodicity, it has everything that you can, and I'll show you. So the map looks like, so 10 slopes, linear sections, you know, and represent the first symbol as 0, 1, 2, 3, and what you do is you start with here. I'm starting with here, and I iterate. I go to 3 by 7, 4. That's what I'm doing on this map, you know. You can have some other thing which will have period 1. You want period 1729, I can give you that. You want period 1, there will be a point here which will be million times, not before. So all periodic orbits are there. And what are these periodic orbits on the decimal representation? They are the rational numbers, right? So initial value, and this is a symbolic sequence. Okay, you don't worry about that. So the this elements of chaos, you have a purely periodic to it, purely periodic. You have what is called eventually periodic. It comes back, right? For example, it goes to 0, right? And this bar 1, 2, 3, 4, 3, 4, 3, 4, 3, 4. It's a shift map, right? You're doing a left shift, you know. So the point I want to say is that this has all, which means that periodic. It's a recurring. There's a periodicity in the expansion, very close to the rational number you will have in irrational, which is not your butterfly effect, right? Small lead to very different behaviors, qualitatively very different behaviors, right? So you have behavior. That's what we mean by chaotic behavior, right? Non-periodic behavior. So the point I want to say is that important to remember, you know, the simple thing you study has all periods as well. So you can repeat. That's the example of a non-periodic orbit on the decimal map, and then it's a way to measure the of nearby trajectories. You remember 2, right? And I showed explodes, one does not explode. Rate of divergence that can be measured with the Lyapunov exponent. That positive, it's chaotic. That's something you need to remember. Now, to decimal expansion, you can do the same thing with binary, right? So if you go, point has a expansion in binary, and remember, its numbers are stored, right? So that's the 1 infinitely of, it just goes on, you know, which you can 0.25 on the computer is what? 0.25 on the digital computer is 0.01. That's it, 0.01. So that's you can do the computation. So this is the you can do ternary and you can do other. So what I'm trying to say is that all numbers they have this behavior, they have these behaviors, and you can have notice that I have a it's continuous but not differentiable, right? I have a continuity here, but I don't have differentiability, whereas in the other continuities, right? So you can have these kind of maps. Now you notice that all these maps belong to maps called they have excellent number theoretic properties. It goes on and Luroth in the 80s and 60s they studied these maps, and in the most general map looks like the most general setting you have notice the solid and the dotted, right? The solid is slope and A1, A2, A3 are uniform or not uniform. In the decimal case you had 10, right? You had A1, A2, A3, A10 and all of them were of length 1 by. Now binary you will have, but in any length, right? And this is called a generalized Luroth series. Now what is very interesting about these maps is you can compute exponent, which is degree of chaos. Remember, more greater than 0 and higher is more, and so you can have weak chaos, you can have strong chaos, and that with the Liouville thing that the entropy symbolic sequence, if you remember that, right? So and if you go P2, P3, P4, right? These are the probability of A2, the probability of being in A3, those are the probabilities, and you can compute the source, and that's you can compute the Shannon entropy, and it turns out there is a nice connection between the chaos and the entropy. Is that I have done a bit of cheating here, which is in when we measure lambda, here we just use logarithm to base 2. That's the I'm writing the exponent in terms of logarithm to base 2. That's the only difference. And the way to interpret this equation is that what information do you get of the initial tree? How many bits of information you get about the initial value? That's what is known as the lambda. Nice connection between them. And what is interesting about these maps is that these maps to do data compression. There's a very coding which is used in JPEG. This algorithm which is already there, it was discovered. We found that it's actually a case of JLS. It's a JLS map. And it has these properties of chaos, which was so it can be used for data compression. And these kind of maps are used as well for compression, for error detection, for computing devices. You can have an XOR gate. You can have all the different logic gates. You can do various things. So I've just there's a paper that I will give you a reference to where it's very, very effective. It's just that people the class with long division, there's chaos you don't know to make. Okay, now what we lay this foundation, what now we'll build that. I'm going to use these two maps for the learning algorithm, and I one of these maps and I get x1, x2, x3. I can keep iterating it. Now, so we're going to use this thing, and the algorithm is very. You have these C1, C2, Cn. That's the and each of neuron, the piecewise linear neuron, it could either Q10 map. It's there, and it's waiting to fire. It's not doing the computation. It's just waiting. The moment an input, it has. We call this Q. And the moment x1 comes in, it starts firing. X2 comes, it starts firing. That there are different lengths, right? This is longer. When criteria here, the moment the trajectory is very close, here the very top. So in other words, what I'm saying is that the neurons will keep firing until they match the stimulus. For example, sending this pixel and it will stop firing when it comes very close to x1. How close? I'll just show you. Yeah, and then what we do is these neural traces. we extract features and then we do a simple, we can have more fancy classifiers. So, it is a very simple algorithm, and we will see that we call this the chaos net. When we introduce this algorithm, we called it, we have modified it slightly, and this is how it works, right. So, activity, which is a hyperparameter, we do not know what the comment firing comes in an epsilon neighbor and the stop firing. So, in this example you can see that it is overshooting, undershooting, and at some point stimulus and then it stops. And the discrimination. So, this discrimination where hyperparameter, again we tune that we say the neuron is on, and below this we say the neuron. So, the three neural activity is one, how epsilon parameter, and the neuron is going to be on or off. So, we have three hyperparameters, and what the guaranteed that of ergodicity, right, in the map which visits all neighborhoods. That means that any stimulus you give, it will visit that. Guaranteed that the algorithm halting problem, right, that will never happen, you know. So, we can choose our, we ensure that, so we have a stopping criteria, and the three hyperparameters, they are, now we do not have, it is a good thing and a bad, have that unfortunately, you know. And find the F1 score or the accuracy, and then go back and change the parameters. I know it is a very stupid, you know. So, we have the three, and so we don't, just do not have that, because notice that each of those neurons are firing at different rates, right. I mean, they are not firing, they are firing at different, some are shorter, some are longer. So, it is not synchronous, you know. So, expression, changing the weights, the have that, you know, and then rate, energy, and entropy. Notice they are very similar to how what neuroscience people, rates of firing of neurons, rate coding, they talk about firing, you know, energy and entropy. So, you know, we have built and we try to you know, do neuroscience on that. Now, interesting. So, what our method does very well on low, it does very well. For higher samples, what we found rates, and that is where we can combine. So, no, either could be combined in series with an ML classifier, you know. We can do either of the two, you know. So, I will show you some results. I mean, again, these are some very simple, I mean, they are test examples, right, test examples. So, just showing you the F1 scores that you get, iris, ionosphere, I mean, and then I am comparing with decision tree, random forest, AdaBoost, you know. So, it is very comparable, and in many cases we do very well as well, and this is the other, so we can also do the hybrid model, right, wherein we combine the chaotic features with the traditional model. So, what we mean by chaotic features that we extract from the neural traces followed by decision tree, chaotic features followed by, that tells you the what if you, but if you use the chaotic, then pass it to % boost in the performance, you know. So, some cases you do not get any boost, but in many cases on their own or the algorithm that you are using, and we also done it with LSTM and CNN and all it here, but for the list, right, we find that in the low training sample we beat CNN, you know, we just beat CNN. this. And then you have the low training sample. Okay, so I mean again I'll skip this part. So some examples. So this is again showing some example where we have SARS-CoV-1, SARS-CoV-2 genome sequences, and that is, and in both well, you know, with just one sample and just independent random trials, and then look at the mean, the average, show that it's just not fitting, right? It's able, you know, in a single sample, and here also it does very well, you know. And if you look at for example in images, you know, you have this again. We're saying that these are number of class. There are only two. But all the ML is the neurocurse learning algorithm, you know. Okay, let me go into some properties now. Now it's important to show that, like for example, layer of you know, carefully chosen can approximate any continuous decision boundary, right? So that function then use, which means it any decision boundary that you want, you know, you could do that, and the proof is not very. It uses the topological in the chaotic system, right? If you take two sets, you know, two open sets of non-zero measure, you will set that's called topological transitivity, right? So to you know, get a proof for this this theorem, and community, we could throw away the GLS and put a Hindmarsh-Rose neuronal model, you know. Nothing changes, you know. So here of course the membrane potential, and we know spike here, and the GLS this time series, because we need a one-dimensional time series, right? So we take this time series which is chaotic, and we have hyper tuning through a cross validation thing, and this actually works. Found is that it does work. Benefit of using this, because from a computational complexity point of view, the 1D GLS neurons are very light. They're very lightweight, right? Operations, you're just multiplying and adding numbers. That's all you're doing, right? It's just a piecewise linear operation, right? So we found this does. If you have a neuromorphic hardware, implement the neurocurse learning using that hardware, you know, because then you could bring in the fact that tune the Hindmarsh-Rose neuronal model in the and then you can get the classification, you know. So it does support that. Okay, so so I think yeah. The other thing I wanted to show, some more things that we have shown, limited training samples. This thing I this right away, right? If you remember earlier, I showed you that we had in deep learning, right? So you can do the same thing with ChaosNet. So in the ChaosNet, you have the neural traces, right? You have the neural traces, and you extract features from that. Bytes and biases. That's your representation vectors, you know. You add learned representation. So similar to deep learning, add Gaussian noise to that, and then see what happens to the performance, you know. And it does. So you notice here around 4.7 decibels, we get 95% accuracy. Deep learning just you know, has a much more faster fall here actually. The ChaosNet also falls, but slightly better than this, I would say, but definitely better. But I mean, we are nowhere at 4 dB. We are at 95%, but once we go below that, I think 4.39 it's 78% accuracy, and then after that. So I think it's. So I think we are. I think my hunch is that chaos is of robustness to noise. You know, there's a lot of studies on that, and the reason. You know, there's some properties called symbolic sequence invariance, certain properties of chaotic systems, which I think that evolution through natural selection. You know, select. So think of it like there was a time when you had all kinds of neurons in the brain, and only those which could be you know, survive would survive long enough to procreate and pass on the genes, and so evolution which are not chaotic, and only those neurons, you know, which could be robust to noise survived, you know. I mean, this is just my theory. So there is reason why there is chaos in the noise, chaos in the brain, you know. Now the other part of the story is noise. So I told you that. Please.
So, as I understand the setup here,
Yeah.
static input is not changing in time, and the chaos unrolls over time.
That's right.
But if you now have a neural system that's all of these kinds of neurons connected to each other,
Yes.
input will also be changing over time.
So here, if you a time series, you pass it in this fashion. You pass it as xn, you know. You pass it like that.
Okay.
So yeah.
So you're then acting on each one. But the thing is, in a real neural system with coupled neurons, if each one of these is
True.
acting in this way,
Right.
its output is going to be varying.
Correct.
And therefore, the input to any other synapse is going to be varying. And when people have done experiments where they've taken isolated synapses and driven them with temporally structured input as opposed to static input, then they see the output of the postsynaptic neurons very reliable. So there's an old Maiman-Szymanowski set of experiments that basically looked at that.
Okay.
And so, like, the question of whether individual neurons are kind of living in a chaotic regime or not, I mean, they might well be, but it might well be that that input is strong enough to overcome the influences of chaos on the spike times.
Okay. So you're saying that in some sense, chaos not designed. Yeah. No, I see your point. Yeah. So it's very interesting what you're saying. Yeah. So, but I mean, but the fact that you know, there's so much of noise in the system, and the chaos system are robust to noise. I thought that the chaos is probably playing a role. You know, and notice how you could the different initial value hyperparameters. You can get different kinds of chaos. You know, so that you could have a richer feature set. You know, so I think chaotic systems in that. Right? Think of it like signal generation, right? It's a signal, very different periods. You can have period 1000, period billion, whatever, which is probably a good representation of the information in the world, right? When you're seeing objects, and so I think it's a nice, you know, rich signal generation. It's not random though. I mean, there's some noise, but I think chaos as a more than anything is my hypothesis. But yeah, we could, yeah. But and by the way, yeah, please go ahead. Yeah, so I'm going to talk about that. Yes. Yes, absolutely. Yes. So that was my part, which I wanted to talk about, the fact that how linear systems and nonlinear systems behave. Not all nonlinear systems, but some nonlinear that when you add some chosen designed nonlinear systems, the performance improves amount of noise, not little noise, though that is called stochastic resonance, you know, whereas they just degrade. And this is actually well studied. This is very well studied. I think goes all the way back, right? In climate science, they studied stochastic resonance, but right. You're they stimulate the auditory nerve. Cochlear implants, if you add noise, it's good for recognition, you know, like perception you said. But also interesting, again, this you know, evolution. There are these amazing examples of paddlefish, this which has these mechanosensory receptors, and what they found is that, and it feeds on the zooplanktons, and if there is no environment, it's able to detect the apnea. If there's no noise, it cannot detect, and if there's intermediate noise, it can detect, you know. So they were had to match the noise in the system, the environment, certain noise. So this selection chose those able to do this SR kind of a behavior, stochastic resonance behavior. And what we remember, the hyperparameter epsilon close is close. That's where SR is, you know, that's where stochastic resonance is. I'll show you this thing. So you can just look at these two plots. So on the left side is the plot with a stimulus basically, and notice how the noise is increasing, right? And then I have a very, it's an animation, right? And what we find is that if you look at this entire performance of the network, how the performance is. It's simple that which gives you this optimal performance, And the reason why, so you may ask why that is the case, and the reason is the following. The reason is that if you have it's very difficult to go on to the stimulus. It keeps on very bad stops, And if you're too, you're going to just stop. It's neural trace which has some interesting features, Again, this is better explanation than this, but the point that I'm trying to make here is that the intermediate noise, that means that this you're seeing this band here. It's the intermediate noise which allows neural traces of the individual neuron and extract and then do the classification, So we find this amazing thing in that we got this. We didn't put stochastic resonance in the system. We just built the. We didn't even know why this was. It took some time for us to realize resonance, and it's. I mean, we should have known better. And I'll give an example. A simple spoken digit. And notice there are some details on how the network is tuned and all that. We do 5-fold cross validation and all that stuff. Notice that again, noise intensity and the performance. But notice how there are local maximas, right? There are local, because it's a very non-convex parameters, right? So it's not a convex thing. But the argument here is these, high, low. That's the stochastic resonance, right? Because what we're saying here is that this is a lower noise, the performance is lower. There is this noise, So we see this kind of real world applications, Yeah.
In the experiment, the previous slide, it's an additive noise, is it?
It is an okay. Okay. The stimulus. So this I'm firing, and I will claim the stimulus if I. It's not. That's important, right? It's like do a stimulus.
We come from communication, and additive noise is what is used everywhere.
Right.
And stochastic resonance does not help us actually there.
Right. Right. So this is not additive. It's about it's I don't know what's the term here. So it's like it's a band of uncertainty, The band it should not be zero, not be very high. It's intermediate. It's the stimulus in a fuzzy manner, That's what I'm saying,
Are you able to confirm that the amount of stochastic resonance advantage using some epsilon parameter?
The epsilon is the hyperparameter, sir. So what we do is for every task, the epsilons are different, Different tasks have different epsilons. Like.
Are you able to increase that advantage, stochastic resonance advantage?
What do you mean by increase? So the example, see this. Look at this. Look at this. Here, notice there are higher noise value, higher epsilon value. That's the SR part here, So I didn't understand your question. Yeah.
Is there a way to
increase it? Oh, that's it. No, sir. I mean, I haven't.
That's the algorithmic aspect.
Algorithm aspect. So you're saying that.
In engineering, we are looking at algorithms.
I think I know that in some examples of even deep ANNs, they add noise to the inputs, for example, right? Something like that, right? To prevent overfitting, to generate. Interpret it like this. It's a matter of interpretation. That the epsilon parameter is the noise, how fuzzy, but I don't know how to answer this. It's a good answer to that. We have to probably work on that, And this again, pass it through our method and then have an SVM, and then you get lots of boost, Again, low. So I'm doing. It's a spoken digit and curves, right? The blue, the black one is Fourier chaos, red one is Fourier. Typically, what we found is using chaotic features from this network boost the downstream ML algorithm, downstream ML, DL, whatever, That's usually the case, So if you take, it's like feature engineering, right? You're using this space to get, which when you feed it to an SVM or a LSTM, imagine that it will work there as well. So if you don't want to classifier, use it, but use our features, through this tuning. And
how do you comment here, because people also use a lot of random projection, right?
So you're right, actually. This is a very interesting question and important question. What about randomness, Now, what is very interesting to understand is what is randomness, It's a very interesting question. And most random, except for probably for quantum tunneling or, see, the problem with random, if it's typically high dimensional chaos, You're using some kind of a iterative, that's what you do, right? You're using some iterative map, and you can find it's a deterministic map. So if you're doing it algorithmically, it's just high dimensional. Then it can be either chaos or, So then this is again sort of a So it's probably epistemic,
That would not be that efficient in terms of in low sample design.
No, so at least my understanding is that what we found is that, see, if you use problem is you will not be. Good thing about these methods is these are reproducible. There's nothing stochastic about it, You get the same result. That's the problem with projections, right? So and
also maybe number of samples might be
numbers also, yeah, that I don't know. But what we found is that low dimensional. I'm using one dimensional chaos, It's as low. Maybe like if you're using a random number, if you're using random projections, right? You're using some high dimensional chaos, whatever, multiple dimensions, highly optimal exponents. That's an overkill, Why would you want to do that? You can just do it with one dimensions. I'm giving you, and if you want, they're very simple, easy to implement also, So I would.
coupling between different input features, right?
So that's an interesting. We did our work. There was something called deep chaos net. They added layers, have a deeper version of this, but we didn't find any benefit, Or rather, we don't know how to do it. We have not coupled actually. So a very dumb way of doing it. We should couple, because what is interesting is when you couple neurons chaotically, synchronization, you have near synchronization, phase synchronization, amplitude synchronization, you have all kinds of stuff, which is important when you have an epileptic seizure, right? There is some notion of synchronization happening, which is not good, right? So that is important. How do we exploit that coupling of these chaotic neurons and use some synchronization to remove noise, for example? Maybe you could use near synchronization, you can remove noise, I think this is all possible. I would say this is just the beginning. I don't think this is a finished product,
So for any special feature, you have to go first in 1D and then use standard CNN kind of method, right? Currently.
We
said the image based, right?
for images,
Pixel and
yeah, that's right.
special
That's correct. So this thing I want to just show, that at this in Europe's paper, we are doing classification. Fine. You can ask us the internal of the data in the network. Do they preserve causal structures or not? This is actually very important, right? We as humans synaptic weights or whatever, you're doing some mapping, but not able to see fire and smoke or whatever. So the question we can ask representation, not only classic. I can say a tiger from a lion, from a sheep, from a goat. I'm doing. And it turns out that that our networks do preserve causal structures, And in terms of we use Granger causality as a. I know it's not. I mean, it's one. And it's not accurate. I mean, it's causality, right? How do you define causality? But a Wiener Granger notion of causality, these networks preserve, whereas LSTN, so the internal neural networks, they don't preserve causality. And the question is why? Chaotic firing, you can see them as composition of chaotic maps. And so it's actually not difficult to argue that these are sort of the causal structures. We are tuning can have this. I want which are these embedded. I can do that, That's what we show in this paper. I think I'll skip. We also did heterogenic. So you could have some are logistic maps, some are we can have different kinds of chaos, because chaos is not just one. There are multiple flavors of chaos, and you can, and heterogeneity also improves. What we found is again boosts performance. Again, I'll skip the results here, but just want to point out that except in one case it really helps in, and what cases is what level of chaos is good, it's always possible. Case where we tune it so that we get the best result. It could have been quasi-periodic work, It's only the best possible, but we could in that we could not find, like weak chaos, strong chaos, because there was a hypothesis by from Wisconsin that weak chaos is good for learning, that not strong chaos. We could not find, it depends on the task, what level of chaos is needed to do the job for us, So just to compare, I think DL and NL, I'm just comparing them. So I think the input activation function, but our output is because the activation is inherent, and then SR, stochastic resonance, is there. I think Vivek is here, so I'm crediting Vivek, so collaborating with Dr. Pawan's group here in Nanoscience Department in ISC. So they did, this is for where is Vivek? Oh, Vivek, you are here. This is for eminence, right? Eminence. So did the I think the numbers are here. So SR, for the same task, we're just comparing. So it's a fair comparison in that sense. Anyway, so I'll just conclude, discuss if there is time. I just wanted to argue that has a role as the hypothesis, and the point I'm trying to say is an interesting thing, because chaos is an interesting interface between physics and biology in this case, right? We talk about neurochaos and neuroscience there. So it's an intersection. It's a very interesting intersection between all these disciplines. But I think this is just the beginning, is what we feel, and yeah. So I mean, I'm going to skip some of this. So we recently have some regression models as well, and implement progress. They're using. I think Vivek will help me more in this AGHB memory, which is able to mimic a biological scenario, like crackling behavior, spatiotemporal avalanches, and stuff like that. So and they're able to implement, and in several cases it does even better than what they find, But it's still work in progress. So we haven't published this work yet. I think with that I will stop, and we can. The codes are all available, by the way. It's all, and I think I just think that there's just one step, just a baby step. We're nowhere, close. All the things the brain is doing, but we'll be able to, build, and we can have hybrid from all models, right? Whether it's transformers or deep learning or NL, and then, but I think these principles we should be able to use to our benefit. Yeah, thank you, and we can take we can break. Yeah, thank you.